Time to do one of those big kind of combined energy problems from chapter 5. It has a lot of different components to it. The one I chose was problem 5.79. This one talks about how we take ethanol and combine it with gasoline and ask us some questions about the energy and the combustion reaction of ethanol. So as we often do from the Brown and Lemay text, we're going to take a look at the problem itself and then go ahead and start tackling the various pieces of it. So here's the problem. They start off with wanting us to write the combustion reaction of ethanol. You notice they don't give us the chemical reaction. They actually want us to write and balance the darn thing. Gosh, that's kind of inconvenient, but okay. So we take the ethanol and C2H6O, and they tell us it's going to combust. Oh man, plus O2. That's what combustion means. And a hydrocarbon, when it's burning, with combusting with oxygen, is going to form, of course, under ideal circumstances, carbon dioxide and water. So yes, it is a basic balancing question. So looking at that for just a second, 2 carbons, that looks pretty reasonable. 6 hydrogens. Now we have 6 hydrogens. That worked out. And then we go, oh please, gods of chemistry, let the oxygens not screw me over. So we look at it and see 2 times 2 is 4, 5, 6, 7 of them here. Over here we only have 3, but yes, if I had 3 of those, 3 times 2 is 6, plus 1 more is 7, 7 oxygens, 7 oxygens. Ooh, that one worked out pretty nicely. So there's the combustion reaction of ethanol written out in balance. That's part A of this particular problem. So on to part B. Calculate the standard enthalpy change for this reaction. Now, this one is going to be the one where you simply look up the enthalpy values, essentially the energy content of each of these molecules relative to the atoms they're built from, compare reactants and products, and come up with a value. This is the one where you have to look up all the different numbers either in the table in the back of the text. You could Google them. Just be careful. The numbers will be ever so slightly different. Depending upon the source or the units that are attached are going to be different. We're going to be using, of course, kilojoules per mole, so do be a little cautious with that. And I should be slightly more careful when I wrote the equation out. I am going to add these. They tell us they add liquid ethanol. They tell us we make carbon dioxide, and since the combustion, we're going to make water in the gas phase. And remember, when you look up these enthalpy values, you will often find that, different compounds will have, are listed in their gas phase and their liquid phase. Water, and I think ethanol is on the table that, from the text we're using, comes out that way sometimes. So do be a little bit cautious. You do have to pay attention, particularly when water is involved, to the state that they are dealing with here, whether it's in the gas phase or the liquid phase. So basically what I'm going to do is just pull up the numbers from the handy dandy table in the back of the textbook. I'm going to look up ethanol, oxygen, CO2, and water in the gas phase and write those numbers down. I'm going to look up their enthalpies of formation. And I have it kind of written over here. When I did that, this is negative 2,777. This one is 0. Remember, elements in their, in their usual state, like O2 from the atmosphere, it has an enthalpy of 0. Okay, good old carbon dioxide, negative 393.5. And then water in the gas phase, negative 241.8. All of these kilojoules per mole. So from these numbers, we can combine them in a certain way and get the enthalpy of the reaction. Okay, they want enthalpy of the reaction here, and this is going to be a classic, and it's harder to say than it is to actually do, but this is a classic products, PROD, products minus sum of the reactants type problem. Now you can write it out in more formal form, but it's just products minus reactants. That's kind of the simple way to remember how to do this, always incorporating the coefficients. I'm going to write the whole calculation out here, and I tend to write down everything very carefully because if there's one source of error when students are approaching these things is when they're calculating away, getting the negative numbers mixed up or something, because there are going to be a lot of adding negative numbers and subtracting negative numbers and all that. And so it is prone to math error. So do be a little bit cautious here. But right at doing the whole calculation, sum of the products, and not S-O-M-E, but S-U-M, sum of the products. I add these numbers, but I add them very carefully. I have 2 carbon dioxides at negative 393.5 kilojoules per mole each, plus 3 waters in the gas phase, negative 241.8 kilojoules per mole. That is the sum of all the product numbers, minus, big brackets again, do exactly this, but over here with the reactants, the sum of the reactants. I only have one of these, so negative 2,777 plus 3. Now, the value is a 0, but I am going to include it simply for completeness, because it, just kind of makes sure I get everything in there. And so that is the calculation I have to do. And so out comes the handy dandy calculator. And I got, when I did this, negative 1,234.7 kilojoules per mole. So it is an exothermic reaction, as you might guess. We aren't going to, use as a fuel source a reaction that is endothermic, that takes energy away. This produces a fair amount of energy as the reaction occurs. Okay, so there's part B. Calculate the standard enthalpy for this reaction, and that means using the numbers you look up either from an online reference or from the table in the back of the text or some other source like that. Products minus reactants, that gets us the number. So there's part B. On to part C. Now for part C, I wanted to make note before we do that one that there is the answer to part B. I just kind of moved it up here to keep it with the rest of the information. Part C is asking us, question mark, how much energy or how much heat is released by the combustion of 1 liter of C2H6O. Okay, how much energy in combusting 1 liter of this stuff? 1 liter. And then you notice they kind of tacked on at the very end of that. Oh, by the way, the density of methanol is 0.791 grams per milliliter. And I'll write that, density of C2H6O. Okay, there it is. All right, so this is going to be pretty much a standard conversion factor type problem. What we are going to do is, and an energy stoichiometry type problem. We're going to need to turn that liter into mass. Okay, once we have mass of ethanol, then it is a classic stoichiometry problem, but we're going to need to use our energy conversion factor here to make this one work. Okay, because remember, what enthalpy of reaction is our way of relating masses and energy in a chemical reaction and expanding the stoichiometry problems to include energy consumed or energy released. And that's what this question is. How much energy is released when you combust a liter of ethanol? Okay. So it is going to require a number of steps to do, but it's pretty straightforward once you kind of see it worked out. 1 liter of ethanol, and I'll just write it out, C2H6O. Of course, they give us the density, 0.791 grams per milliliter. So that is going to require me to get my little fingers on milliliters. This, of course, is pretty standard stuff. We learned this back in 1145. There are 1,000 milliliters in a liter. So now I have milliliters of ethanol, which means I am one step away from 1 milliliter, 0.791 grams. C2H6O. Now I have grams of ethanol. Now I'm ready to do the stoichiometry problem. And so, of course, for the stoichiometry problem, you turn grams into moles. Step 1, turn grams into moles. Grams C2H6O, moles C2H6O. Yes, moles, grams, and I'm writing grams and moles of exactly what I'm talking about each time because it has helped me keep straight all the different numbers that get flying around out here. And so the molecular weight of this thing, 1 mole of this is, oh gosh, I don't think I had that in my head. 12, 24, 24, 34, 5, 6, 7, 38, 42, 43, 44 grams per mole. And I'm going to check that. It's a good thing I did because it's 46 grams per mole. I could have done that old, oh look over there, but no, I screwed that up. But I got to take care of. All right, so now we have the number of moles of ethanol. Now, in my way of doing these types of problems, remember, when it's an energy calculation, how much energy, it's an energy stoichiometry problem, I convert moles of our reactants or products into moles, what I call moles of reaction. 1 mole of reaction is involved in every chemical reaction. That is written with the smallest whole number coefficients possible. That is this one here. And so 1 mole of ethanol is involved in 1 mole of reaction. Okay? And then that allows me to use that. Okay? 1 mole of reaction gives me 1,234.7 kilojoules of energy. Okay? And I'm going to address the negative sign in just a second. But now I have this big old calculation to work out on the calculator. And what I got when I did it, assuming I did it right, which is always questionable, is 21,178 kilojoules in 1 liter of ethanol. Okay? Now, 21,000 kilojoules of energy, of heat, are going to be released when we combust a liter of ethanol. Now, the question a lot of students will have, and textbooks vary on this one, is what do you do about that negative sign? Ooh, I didn't include the negative sign here. I have seen some textbooks and some, solution guides put that negative sign in and write this as a negative number. To be honest with you, I don't really like having a negative number in there because the way the question is phrased and the way the answer comes out implies 21,000 kilojoules of energy released. That's what the negative sign is there for. We use negative signs to indicate exothermic reactions, energy releasing processes here. So yes, negative 21,000 kilojoules is a way of saying 21,000 kilojoules of energy released. But frankly, by just saying 21,178 kilojoules of energy are released when a liter of ethanol combusts, it pretty much exactly conveys the same thing. So to be honest with you, whether you have, for my purposes, whether you have the negative sign in there or not, I really don't care, as long as you have it very clear that this is the amount of energy released, okay, when a liter of ethanol combusts. So there's part C. And now, one last part to go. Okay, we're going to move on to part D. Okay, back in a moment. Part D. Now, part D is actually almost a repeat of part C, except it's asked a little bit unusually. I don't see a question in this direction very often. That's why I kind of chose wanting to do this one. They are asking now, what is the number of grams, question mark, grams CO2 for every 1 kilojoule produced? Okay, that's the question in part D. Okay, how many grams, what is the mass of carbon dioxide formed in this process when a kilojoule of energy has been produced? Okay, now, like I say, it is an energy stoichiometry problem. It's going to look a lot like part C, but it does require a little bit of different thinking about it here. So what we are after, applying our old standard of kind of how we approach these things, when we're done, we're going to have grams of carbon dioxide. And given this is the energy chapter and this is an energy stoichiometry type problem, you can bet we're going to have moles and all the other sorts of stuff in this calculation. We have to look for our starting point. And a starting point is actually the 1 kilojoules. A lot of students will want to try to start here. That is trying to start with a conversion factor. It can be done, but I think it's easier to start with a number that doesn't have the 2 units on it, and this one qualifies here. And so if I write this out front, then I hope it kind of like, oh, what I need to do is convert kilojoules into moles, moles into moles, moles into grams. There's the basic structure of the stoichiometry problem. And remember, when we talked about stoichiometry problems, the first step is always convert whatever you're given into moles, okay? Often we're given masses, and so it's a molecular weight conversion, but we don't have to be given masses. In that last one, we were given, in part C, we were given volumes, so we had to use density to turn it into mass, and away we go. Here, we're given energy, but we know how to turn energy into moles. It's the enthalpy value. So we're going to turn this energy into moles of reaction, into moles of reaction into moles of carbon dioxide, moles of carbon dioxide into grams of carbon dioxide. So away we go. 1 kilojoule of energy. And to get the kilojoules to work out, they're going to go on the bottom. Moles of reaction, therefore, will be on top. And the number is 1,234.7 kilojoules of energy for each mole of reaction. Okay? Now, 1 mole of reaction, and remember, when I say 1 mole of reaction, I mean the chemical equation written with the smallest whole number coefficients. That's what we have here. Features, 1 mole of reaction features 2 moles of carbon dioxide, coefficient 2. Once I have the 2 moles of carbon dioxide, then, we're really off to the races now. 1 mole of carbon dioxide is, of course, 44, and that one is 44, grams of carbon dioxide per mole, okay? So there's a simple 3-step stoichiometry problem, okay, for part D. It's actually a little bit easier than part C was. And so we go ahead and do another magic calculator, punching out on our calculators, and we get 0.713, okay? Not much, okay? So to release a kilojoule of energy, we don't have to burn up much. We don't get a lot of carbon dioxide for just 1 kilojoule, but of course 1 kilojoule is really a fairly small amount of energy. We need a lot of energy to do anything useful. So there's the energy stoichiometry problem for part D. So together, parts A, B, C, and D incorporate a lot of the chapter 5 stuff here. Write an equation and balance the thing. That's a chapter 4 type topic as well. Part B was the standard enthalpy calculation, unique to this chapter. The last 2 were energy stoichiometry problems. Stoichiometry, a topic of chapter 3, but now with this new conversion factor, enthalpies that relate masses and moles to energy in a chemical reaction. Remember, energy, the other reactant or product in a chemical reaction that can be treated just like any other reactant or product in doing these types of calculations. So look that over, practice a few of these on your own, and we'll talk to you later.